Right, well, thanks for inviting me to give a talk. And I'll be talking about, starting with some motivation and then talking about how we can treat mineralogy self-consistently in these types of convection models. And then I'll be talking about mantle thermochemical evolution from convection modeling, the effect of composition, the effect of, various things. And then finally, talking about the seismic signature of the models and comparing that to actual models. So firstly, compositional variations are certainly important in the Earth. We see them in outcrops of rocks that are thought to be mantle rocks. Geochemistry tells us that there are several N members that must exist somewhere in the mantle. Seismic tomography, this is the probabilistic tomography of Deschamps et al., indicate that there's substantial heterogeneity due to compositional variations. This is comparing the variation in density due to temperature on the left and composition on the right, similar amplitude. And we even saw in the first talk this morning how even when you're trying to force as much of the heterogeneity as possible to be explained by temperature, you still end up with density variations due to composition similar to those due to temperature at the very base of the mantle. And in a study by Frédéric Deschamps and myself in two papers, we compared various convection models with this probabilistic tomography, finding out which ones fit best. And these are two sort of good-fitting convection models. Green is composition, and this is temperature on the right. And what you see is that the models that fit best have these sort of piles or sometimes ridges of dense material existing above the core mantle boundary. And that's just an elaboration on that. So, and various other lines of evidence, such as it was summarized in the first talk this morning, indicate that there might be large-scale compositional variations in the deep mantle. So the question is, where does it come from? And there are two possibilities. One is it could be generated over time, and the main sort of mechanism for that, or one of the main ones, is recycling of oceanic crust. Another one, which the next speaker will talk about, is crystallization of a basal magma ocean. Another possibility is that there was always dense material at the base due to one of several mechanisms, and that over time it's just gradually been entrained. And there are various cartoon models that show, how compositional variations could exist in the mantle and evolve over time. I won't go through all of these, but most likely it's not just one of these. There could be more than one source of compositional differentiation. So, for example, here, this could represent the early Earth, where you have some sort of melting in the upper mantle, and if the melt is denser than the solid, it will migrate downwards, forming a dense solid that could gradually drip or fall to the bottom somehow. You could have this basal magma ocean that we'll hear about shortly. You could have slabs coming down and differentiating at the bottom. So you probably have a mélange of material at the bottom. So this is the basal mélange, I refer it to, or BAM for short. So, and then later on, by the present day, we have probably got large accumulations of compositionally heterogeneous material, this basal mélange, formed from various products. But let's focus particularly on recycling of oceanic crust. So over geological history, you can estimate the volume of oceanic crust that's been subducted, and if the present-day production rate was valid, it's about 10% of the mantle volume. If the rate was higher in the past, proportional to heating squared, it would be about 50% of mantle volume. So, in any case, there's a huge amount of oceanic crust that's being produced and subducted, and this also means that most of the mantle should have passed through the mid-ocean ridge melting environment and been processed or compositionally differentiated. So we expect almost no unprocessed material in the mantle. Anyway, when the slab is compositionally stratified, and when the slab comes down and reaches the core mantle boundary, green is basalt here and blue is Harzbergite, some of the basalt can separate from the slab and join a potential pre-existing layer of basalt. And exactly, it depends on various parameters, there's models later on. This shows the fraction of the basalt on the slab that is in the deep mantle, and you see that some fraction of it seems to remain behind for a long time. Not all of it, but sort of in the tens of percent perhaps. And various people have modeled this in the global context, global convection models where you produce oceanic crust and Harzbergite and it goes to the bottom, and some of it segregates out at the bottom. There's Davies, some models by Ogawa, and some of our own models, where this is temperature, this is composition, red is crustal material that's been subducted to the bottom and has segregated out. So now I'll talk more about these types of models where you can model the evolution of the mantle. So one of the key things is that these include melting, which produces the crust. Other things are, okay, that the viscosity. We heard this morning that we've got no idea what the viscosity dependent on various parameters is, but anyway, we assume some law dependent on temperature, depth, and stress. They have plate tectonics induced by yielding. They have decaying radiogenic elements. The core starts off hot and cools with time. They're compressible. There are several papers, and I'll touch on some of the main findings in the next few minutes. So a typical time evolution is like this. This is temperature. This is, on the bottom is composition. So you see at the bottom you get some accumulations of this dense subducted crust. Generally the mantle is bluish, which means it's average composition of pyrrolite. Dark blue is Harzbergite. And actually, fairly early on, you establish a sort of equilibrium size for these piles of crust, and they remain more or less the same over geological time. See, there's billions of years passing here. And actually, the amount of basalt that settles at the bottom depends very much on the density contrast between the morb and the other stuff. So at the top we have a model with no density contrast between morb and other stuff, and you don't get a layer building up, you just get heterogeneity everywhere. This is a large density contrast, and you get an almost global layer. This is intermediate. This looks more like what people think might be appropriate for the Earth. So now we'll talk about the mineralogy. And in these, well, it's been established over the years that phase transitions can be important in influencing mantle convection, and they're often sort of inserted individually. So each phase transition will be, put in by hand. But actually, the mantle mineralogy is quite complex, and Michael Kendall showed a couple of diagrams like this earlier on, which shows the different phases that exist as a function of depth. And this is just for one particular, I think this is for pyrrolite. So there are actually many phase transitions, and this also depends on composition. So rather than manually try and insert complex diagrams like this, it's convenient to calculate by minimization of free energy what the assemblage of stable phases is for at a given composition, temperature, and pressure. And so for this, we use the package called Perplex by Connolly. And what you do is you specify the composition in terms of 5 or 6 oxides, the temperature and the pressure, and it finds the stable minerals, and then computes the overall properties of the assemblage, which you can generate lookup tables of density and enthalpy and insert them into convection models. So this shows that. So you basically use this to compute lookup tables of, say, density as a function of pressure and temperature for a given composition, and then we can use these in the convection models like this. So in our 2009 paper, yes, we compute the evolution of the mantle over billions of years. So this is compositional anomalies, this is also composition, this is temperature. And actually in that study we found that the general behavior is not much different from what we obtained with a much simpler parameterization. But anyway, continuing, okay, that's just other pictures. Well, one of the things is that the compositions are somewhat uncertain, particularly mid-ocean ridge basalt. I mean, it depends where you measure it, and it also is probably not, it hasn't been constant over geological time, and it's not even constant over the depth of the oceanic crust. So what we did is to run the same types of models with 4 different compositions of morb. listed here from four different sort of studies, and see what difference that makes. So I mentioned lookup tables, and this is the type of lookup table that you get. This is the difference between the Morb density and Harzburgite density as a function of depth and temperature for the different compositional assumptions. And what you see is that Morb is generally denser, but actually it can be less dense in a certain pressure and temperature range below 660. But the exact difference varies with the assumed composition of Morb. And so when you go ahead and compute long-term evolution with these different compositions, you get somewhat different results. Some of them produce far more layering than others. And that's because, yes, the density contrast depends on composition, and that influences the amount of layering. As you can see in this, which is a radial profile, so this is the percentage basalt as a function of depth, and for example, this model of Morb composition produces very strong layering, whereas this model produces much less layering at the bottom. So this is a bit troubling that things are so sensitive to, what happens is so sensitive to uncertain parameters, but okay, certainly then this is important. So in fact I already covered this, that's not quite right. What should be highlighted is the next line. Because mantle convection basically influences the geodynamo very strongly. Because mantle convection controls the heat flux out of the core. And of course, if the heat flux is too low, you can't actually have a dynamo. So, some other planets, Venus and Mars, don't have a dynamo at the present day. So this is, a real possibility. And this layering that sometimes occurs above the core mantle boundary actually reduces the heat flow from the core. So what we studied is a couple of things. Well, one is the effective basalt density, as I mentioned before, and also a couple of parameters related to the core. One is the amount of radiogenic heating in the core, because it's been proposed that there might be some radioactive potassium in the core. And the other one is the initial core temperature. And, okay, so this shows the mantle for two different initial core temperatures. This is a relatively low initial temperature. This is high. And time goes from left to right. So what you see is that at the present day, there's not a significant difference in the character of these solutions, right? But early on there is, of course, with the high core temperature, you get a lot more melting early on. But after billions of years, things have sort of reached an equilibrium. And we find the same thing when we look at time series. For example, this is CMB temperature as a function of time. After 4.5 billion years, the cases have all converged to more or less the same CMB temperature, regardless of the initial temperature. But what we're interested in here is the core. So this is the heat flux out of the core. And as you see, it's high early on and decreases with time. And again, if this drops too low, then the dynamo could shut off. On the other hand, if this is too high, then the core cools more. And what happens is, when the cool reaches a certain temperature, is that the inner core starts solidifying. So this shows inner core size. So at some point, you start forming an inner core, and it gets bigger and bigger. And in all of these cases, it's too big, actually. The correct size would be about here, 1,100 kilometers. So in these simulations, there's too much cooling of the core. The inner core is too large. So somehow we have to strike a balance. We have to extract enough heat out of the core to allow a dynamo, but not so much that you get too much core cooling. And compositional variations in the deep mantle play a big role in this. So too much core cooling in this case, which corresponds to these. So one thing that helps, actually, is having radiogenic heating in the core, because it allows a higher heat flow out of the core without cooling it so much. So in these cases, we look at the graph of inner core size, and we see that there's no inner core until right at the very end. So this has not enough core cooling, but this is quite a lot of potassium-40. I think this is 800 parts per million. So it's obviously a happy medium here, which will allow us to get the correct amount of core cooling while still keeping a dynamo going. Another thing that's very important is the density contrast of basalt in the deep mantle. I showed this before. So this is high density contrast, this is zero density contrast. And we can actually see this. This is with very dense morb. And here the CMB heat flux drops to close to zero. And this is ohmic dissipation in the core. It actually drops to zero. So here the dynamo shuts off. So this is not very realistic for Earth. So this is an argument against having a sort of global layer above the core, because you might not get enough heat flow to allow a dynamo. And this is with the sort of intermediate morb density contrast. No, this is with neutral morb, and you get too much cooling again. So there's this balance between the different parameters. Like initial core temperature is not important, but the amount of potassium in the core is very important, and the density contrast of morb is very important. Again, in allowing you to have a dynamo over geological time without too much cooling and too large an inner core. So this is just two successful cases. Anyway, now John Brodholt this morning talked about post-perovskite and that it might be weak. So we did a comparison here where we compare a simulation with post-perovskite having the same viscosity as perovskite, and here's one where it's weaker by a couple of orders of magnitude. And surprisingly, it does make actually a very big difference. Even though this is restricted to a small area above the core mantle boundary, you can actually affect the global heat flow. So this is the core heat flow. This is with the weak post-perovskite. So you can substantially increase the CMB heat flow and also the heat flow at the surface just by having this weaker post-perovskite. So perhaps surprising, but this emphasizes the importance of the work that John is doing, and or something. Anyway, thank you, Paul. Let's get to the seismic signature. So it's fine to run these models and produce nice pictures, but we need to compare them with observations. So again, this is just using the latest database. Okay, so. And one of the questions is, which I know will be addressed later as well, whether you can generate seismic observations with purely thermal convection or whether you need compositional variations. So this is an example of a purely thermal convection case. It's temperature. And this is the S velocity, and this is the bulk velocity. And what you can see then is that, of course, slabs are fast, and plumes are slow. But where the slabs reach the core mantle boundary, you actually get these regions of very fast material, which is post-perovskite. So you can actually see post-perovskite having a large influence on the seismic signature in the deep mantle, in S velocity, not bulk velocity. And so when we can plot radial profiles along these different lines, and so this is VS, sometimes you get this region of post-perovskite, sort of double crossing. Sometimes you miss it, just as in some cartoons that we saw earlier. And this is the bulk sound velocity, which goes the other way. Okay, well, this is a thermochemical case. And what we see here is, again, you get accumulations of basalt. They're hot. And then we look at VS and VB, bulk velocity. Again, you see that these cold regions have post-perovskite, so they're very fast. The regions with morb are actually slow, despite the fact that morb is intrinsically faster because they're hot, which overpowers the other effect. So you get quite a strong natural variations in seismic velocity above the core mantle boundary. And when we draw some profiles through these, you get. Sometimes you can see post-perovskite as before, but you also see these other discontinuities sometimes cropping up. There are a bunch of other cases which I won't go through unless someone asks questions. But this analyzes some of the discontinuities that you can see. So this is perovskite, or post-perovskite, and this is crossing basically layers of basalt in the slab, where the slab reaches the bottom and it sort of folds. And you can actually have multiple crossings of the basaltic layer in the slab, which might appear as seismic discontinuities. And this is, different, just various different models. So discontinuities in the deep mantle are not necessarily caused by a phase transition, although they can be. This shows profiles inside piles of basalt, and you do seem actually to have some sort of feature here, which could be the post-perovskite transition occurring at a shallower pressure. So, yeah, from these you can see that piles of basalt are still slow in Vs, that one thing I didn't mention is that post-perovskite actually introduces an anti-correlation between the S velocity and bulk velocity, which you can see, for example, here. It goes, S velocity goes up, bulk velocity goes down. I mean, that would occur was pointed out a number of years ago. We're certainly seeing that. Right. So finally, in the last few minutes, I can talk about some synthetic seismic tomography, which is presently being worked on by Ludwig Auer and Lapo Boschi. And so the idea here is we take the results from the convection model and do what's known as a seismic filter, which is something that various groups have done since the 1990s, where you sort of simulate the processing that people use for seismic tomography, and so you come up with what seismic tomography would image your model as. And this is input, P and S. This is the inversion of actual data. So these are real models of Earth. These are the synthetic models of Earth. So comparing thermochemical to isochemical. And, I mean, these are very preliminary results, but I'll just highlight a couple of things. So these are histograms of the anomalies of P or S at just above the core mantle boundary. And this is the full sort of unfiltered model. What we see is that they're for thermochemical convection, which is the top row, they're generally bimodal. Right, so this is S, the thermochemical model. We get a big peak here and a smaller peak here. This is P. We also have a peak here and a peak there. For isochemical models, it's not so bimodal. It's more a peak with a long tail. But then after it's gone through this tomographic filter, we've actually lost the bimodality. So here, for example, it's got a peak with a tail, so it's skewed. So we've lost the fact that it should have two peaks. And the same with the P tomography. It should have a hole here, but it doesn't. So, and then with these, yes, it's basically spread it out. And then we can compare this to real seismic tomographic models. So here the synthetic model, so thermochemical on the top, isochemical on the bottom. And these are various, P is green and S is blue. And yes, here you see actually that the real seismic tomographic models also seem to have a peak with a tail to the left. And they look, if you compare these, to my eyes, these tomographic models look more like the thermochemical model over here. The isochemical model has the skew to the wrong side. So, again, based on this simple comparison, it seems like the histogram of seismic anomalies is better reproduced by a thermochemical model, and in reality, you should probably have a bimodal distribution, but the tomography can't recover that. We can also look at the heterogeneity as a function of depth. So this is depth. This is the log of the power, log 10, and this is S mean. This is the actual data inversion for this particular study. And these are the two Mantle convection models, thermochemical, isochemical. So they both look not too bad, actually. Arguably, the isochemical has too little power, and the thermochemical looks as if it might have too much power. But when we plot radial profiles of RMS heterogeneity, you actually find, let's look at S, that, yes, in the sort of unfiltered model, S definitely has too much power. But after the filtering, you seem to lose this peak at the bottom, and it ends up sort of being very close to the model based on actual seismic data. Whereas the isochemical model, the amplitudes are a little bit too small. Right, which brings me to the conclusions. So compositional variations are important. We could have this layer of of mélange, spatial mélange, BAM at the bottom. One thing that's not important, at least in these models, is the initial core mantle boundary temperature, things that are important to the density of mid-ocean ridge basalt at the bottom, the viscosity of post-perovskite, the fact that post-perovskite produces strong seismic heterogeneity and an anti-correlation between VS and VB. Seismic discontinuities can be compositional or phase. Seismic tomography seems to lose a sort of bimodal signature that should be there, and at least based on this one model, which is all we've looked at so far, it seems like you can fit the histogram of tomography and the amplitude by thermochemical models. Okay, thank you.